Here is one of the wildest true stories in all of space science. Easily a 9. 5 out of 10 on the scale of things that sound completely made up, but are not. And the question tonight is simple. Where will Voyager 1 actually be 1 trillion years from now? Let's start easy. Right now, Voyager 1 is the most distant object humans have ever built, drifting through interstellar space more than 15 billion miles from Earth, moving at roughly 38,000 miles per hour. And it is slowly dying, losing about 4 watts of power every year, meaning sometime in the early 2030s, its last instrument goes silent forever. But here is the twist. That silence is not the end. It is barely the beginning. Because once Voyager 1 stops transmitting, it does not stop moving. It does not rust. It does not burn up. Nothing out there can destroy it, so it keeps going forever. And that single fact is what tonight is really about. Voyager 1 launched on September 5th, 1977 from Cape Canaveral, Florida, carrying a golden record loaded with sounds of Earth, whale songs, greetings in dozens of languages, and music from cultures around the world, a message in a bottle thrown into the largest ocean imaginable. It was originally built to study Jupiter and Saturn, finished that job, and kept going. In August of 2012, it crossed the heliopause, the boundary where the sun's solar wind gives way to true interstellar space, becoming the first human-made object to ever leave the solar system's protective bubble. A radio signal from Earth now takes more than 23 hours just to reach it, one way. And once its power runs out completely, Voyager will transform from an active mission into a silent, unpowered, unguided metal object, traveling through the galaxy longer than anything else our species has ever created, longer than our species itself, longer than the sun. Let's start with the near future, because even this part is strange enough on its own. In about 40,000 years, Voyager 1 will drift within roughly 1.6 light years of a small red dwarf star called Gliese 445. Not a visit, just a distant pass. About 296,000 years from now, it will pass within around 4.5 light years of Sirius, the brightest star in our night sky. Again, no encounter, just 2 objects briefly sharing the same small patch of the galaxy before drifting apart. 40,000 years sounds enormous by any human standard. Hold on to that number, because everything that follows is going to make it look like nothing at all. Voyager is no longer bound to our solar system. It is bound to the galaxy itself now, essentially its own tiny planet slowly orbiting the center of the Milky Way, the same way Earth orbits the sun, just on a far larger, far slower loop. And tonight, we are tracing that loop all the way out to 1 trillion years. To understand what happens to Voyager, we first need to understand what happens to everything around it, starting with home. In roughly 5 billion years, our sun will run out of hydrogen fuel in its core, begin fusing helium instead, and swell into a red giant, its outer layers expanding to engulf Mercury, then Venus, and quite possibly reach all the way to Earth's orbit. By that point, Earth will almost certainly be uninhabitable, its oceans boiled away, atmosphere stripped, surface scorched. But here's the thing. Voyager by then will already be so far from the solar system that none of this touches it at all. It left the sun's gravitational influence behind long ago. It will not feel the sun's death as heat or light. It is simply too far away, drifting indifferently while its home star sheds its outer layers into a glowing planetary nebula, and its core collapses into a white dwarf, a dense ember about the size of Earth that will then cool for trillions of years. And Voyager will still be out there when all of this happens, a tiny relic from a civilization that no longer has a home star to return to. Now push the timeline further into the trillions, and something even stranger takes over. Star formation itself is only a temporary phase in the life of the universe. Stars form from clouds of hydrogen and helium gas, and every time a new star is born, some of that raw material gets locked away permanently, either burned through fusion or scattered as heavier elements that do not easily form new stars again. Over time, the galaxy's available supply of star-forming gas steadily runs low. Astronomers currently estimate that the very last new stars capable of forming will appear somewhere between 1 trillion and 100 trillion years from now, with red dwarfs, the smallest, most fuel-efficient stars, being the last ones still lit, because red dwarfs burn their fuel so slowly that some forming today could still be shining 1 trillion years into the future. Which means when we ask where Voyager will be at that point, we are not asking about some distant dead husk of a galaxy. We are asking about a period when the last generation of stars may still be faintly flickering in the dark. Here's where it gets bigger, and this is the part where the story stops feeling like Voyager's story and starts feeling like the galaxy's story instead. By that point, the Milky Way will not exist anymore, at least not in the shape we recognize today, because our galaxy and the nearby Andromeda galaxy are currently moving toward each other at roughly 250,000 miles per hour. And current estimates suggest the two will begin merging in about 4.5 billion years, fully settling into a single combined galaxy, sometimes nicknamed Milkomeda, over the following several billion years after that. During this merger, individual stars almost never actually collide with each other directly, because the space between stars, even within a single galaxy, is so vast that the odds of two stars actually striking one another are close to zero. Instead, gravity simply reshuffles everything, flinging stars into entirely new orbits, some ejected completely out of the merged galaxy and sent drifting alone into intergalactic space. Voyager, by this point already ancient beyond any human frame of reference, gets caught up in the same reshuffling too, not as a star, but as a tiny piece of debris following whatever gravitational path the collision assigns it. There is a real possibility, though not a certainty, that Voyager could end up ejected from the merged galaxy entirely, flung out into the vast emptiness between galaxies. Or it could remain bound to the merged galaxy, tracing enormous loops through it for the rest of its existence. Honestly, scientists cannot say for certain which outcome will happen, because we are talking about gravitational interactions playing out over timescales so long that even our best computer simulations carry enormous uncertainty. But here's what we can say with real confidence. Voyager will survive the merger itself. There's essentially nothing in intergalactic space capable of destroying it. Now picture what the sky itself will actually look like by the time we reach the 1 trillion year mark, because this is where things get genuinely unsettling. The universe is expanding, and that expansion is accelerating, driven by whatever we currently call dark energy. Right now, we can see galaxies billions of light years away, their light having traveled across almost the entire history of the universe just to reach us. But as the universe keeps expanding, more and more distant galaxies will eventually cross something called the cosmological horizon, a boundary beyond which their light can never reach us again, because the space between us and them is stretching faster than light itself can cross it. Astronomers estimate that within roughly 100 billion years, nearly every galaxy outside our own local group will have become permanently invisible, their light redshifted into nothingness. By the time we reach 1 trillion years, this process will be long finished. The night sky, if anyone were even there to look up, would show only a single merged galactic structure, our own, and beyond it, nothing at all. Total darkness. No other galaxies, no cosmic web, no distant light whatsoever. Just isolation on a scale that dwarfs anything we currently experience. And Voyager, drifting somewhere in or around whatever remains of that merged galaxy, will exist entirely inside that darkness. There will not be many recognizable stars left at that point either. By 1 trillion years, most sun-like stars across the universe will have already exhausted their fuel and collapsed into white dwarfs, dense Earth-sized embers slowly radiating away their leftover heat into space. These white dwarfs cool incredibly slowly, taking on the order of quadrillions of years to eventually cool all the way down into what astronomers call a black dwarf, a completely cold, dark, inert remnant that no longer glows at all. So at the 1 trillion year mark, most white dwarfs will still be faintly warm, glowing a dull, deep red rather than our sun's current bright yellow-white light, while the red dwarfs, still burning at that point, will be dimmer, sipping their hydrogen so slowly they are expected to remain lit for tens of trillions of years before finally exhausting their fuel too. If Voyager happened to drift near one of these dying stellar embers, its instruments, long since silent by then, would not register anything. No camera capturing images, no sensor reporting data. It would simply pass by quietly, a small piece of cold metal gliding past a cooling star inside a universe that has almost entirely gone quiet. Here's a question worth sitting with, and it's one most people never think to ask. Would Voyager even still be recognizable as Voyager after 1 trillion years? The honest answer is probably yes, structurally, though almost certainly not electronically. There's no atmosphere in deep space to erode it, no water to rust its metal frame, no biological process capable of breaking it down. Micrometeorite impacts remain possible, but statistically extremely rare given how staggeringly empty interstellar space actually is. Even so, over spans of time this extreme, even small effects genuinely add up, since cosmic rays, extremely high energy particles traveling at close to the speed of light, will continually strike Voyager's surface, slowly degrading its materials at the atomic level. The golden record itself, plated in gold and specifically designed to resist exactly this kind of degradation, was built with precisely this scenario in mind. Which means Voyager's basic shape, its antenna, its instrument booms, its main body, would still exist in some form, pitted and worn by radiation, but not vaporized, not destroyed. Simply old, beyond any concept of old that makes intuitive sense to us today. So where physically would Voyager actually be? This is the part where we have to be genuinely honest about the limits of prediction. Its exact position after 1 trillion years depends on an almost incomprehensible chain of gravitational interactions. The merger with Andromeda, possible ejections and recaptures during that merger, further mergers with smaller nearby galaxies expected to be absorbed over the following tens of billions of years, and the slow, chaotic churn of orbits within whatever galactic structure eventually settles into place. Nobody can give exact coordinates, because the uncertainty simply compounds too much across that length of time. But we can describe the realistic range of likely outcomes, because gravitational physics itself does not change, even if we cannot track every variable perfectly across a trillion years. One possibility places Voyager still orbiting slowly within the combined body of the merged Milky Way and Andromeda, tracing an enormous, incredibly slow loop through the galaxy's outer regions, a single orbit potentially taking hundreds of millions of years, meaning Voyager would only complete a small handful of full orbits across the entire span between now and the 1 trillion year mark. Another genuinely plausible possibility is that gravitational interactions during the merger fling Voyager out entirely, sending it drifting into intergalactic space, no longer orbiting anything at all, simply continuing in something close to a straight line through a void so empty it might never encounter another significant gravitational structure ever again. Either way, Voyager is not really heading toward a destination in any meaningful sense. There is no arrival waiting for it. There is only continuation. It genuinely helps to think about scale here, because 1 trillion years is not simply a bigger version of 1 million years. It is an entirely different category of time altogether. The universe itself is currently about 13.8 billion years old, meaning 1 trillion years is more than 70 times the entire current age of the universe. If you compress the full history of the universe from the Big Bang until today into a single day, 1 trillion years would still stretch more than 70 additional days beyond that point. Everything that has ever happened, every star ever formed, every galaxy ever observed, every moment of human history, fits into a sliver of time so small compared to 1 trillion years that it barely registers as a meaningful fraction at all. And Voyager, the small human-built machine, is expected to simply keep existing, keep moving through nearly the entirety of that unimaginable stretch. Not operating, not sending signals, not doing anything in any active sense, just persisting. A fixed physical object, obeying the same basic laws of motion that carried it out of the solar system in the first place, carried along now by gravity on a scale far beyond anything its original creators ever imagined when they bolted its instruments together inside a clean room in California. There is something truly worth pausing on here, and it is not really about physics anymore. It is about what Voyager genuinely represents right now in this exact moment. Voyager 1 is the farthest reaching physical expression of human curiosity that has ever existed. Every civilization before ours built things meant to last. Pyramids, cathedrals, monuments carved directly into mountainsides. And every single one of them, without exception, is temporary on a truly cosmic scale. Wind and rain and time erode stone. Empires eventually fall. Entire languages disappear completely. But Voyager, sitting in the near-perfect vacuum of interstellar space, protected from almost everything that destroys ordinary objects here on Earth, is arguably the single most durable thing humanity has ever built, precisely because it was sent somewhere that nothing much ever happens. By the time it potentially reaches the 1 trillion year mark still intact, it will have outlasted our sun by hundreds of billions of years. It will have outlasted our entire species, almost certainly, along with every language we have ever spoken, every structure we have ever built, and every memory we have ever recorded, except for that small collection of sounds and images etched permanently onto the golden record, which by then may be the only remaining evidence that humanity ever existed at all. Let's be honest about the uncertainty here too, because good science means openly admitting what we do not actually know. We cannot say for certain Voyager will avoid every possible collision over a timescale this long, though the odds strongly favor it given how staggeringly empty interstellar and intergalactic space really are. We cannot say for certain exactly where the galactic merger will ultimately place it, whether safely inside the merged galaxy or flung entirely out into the surrounding emptiness. We cannot say with total certainty exactly how accumulated radiation damage will affect its structure after such an extreme span of time, only that current physics strongly suggests it should remain largely intact in overall shape, even once every working part of it has long since gone completely silent. But here's what we do know with a fairly high degree of confidence. Voyager will still exist in some genuinely recognizable form, still moving, still obeying the exact same fundamental laws of gravity and motion that have governed it since the moment it first left Earth, because there is simply no plausible mechanism based on everything we currently understand about physics that would erase it entirely before then. So picture it, 1 trillion years from now, and stay with this image for a second. The sun that originally launched Voyager is long gone, its material scattered or permanently locked inside a slowly cooling white dwarf ember. Earth itself, If any trace of it remains at all, is completely unrecognizable and possibly no longer exists as a distinct body whatsoever. The Milky Way and Andromeda merged into a single galaxy so long ago that the event itself has become ancient history, even by the standards of that distant era. Most of the stars ever capable of shining have already gone dark, the very last red dwarfs finally sputtering out, leaving behind a galaxy filled mostly with cold, silent remnants drifting through empty space. The sky, if anyone were somehow there to observe it, shows no other galaxies at all, the entire rest of the observable universe having drifted permanently beyond the reach of light long before. And somewhere within that darkness, whether slowly looping through what remains of the merged galaxy, or drifting alone through the emptiness far beyond it, a small metal spacecraft, its instruments silent, its power completely gone, its golden record still faintly reflecting whatever dim light happens to fall on it, simply continues on, not moving toward anything in particular. Not moving away from anything either, simply continuing. Exactly the way it has continued since 1977, obeying the same laws of motion, carrying the same message, entirely indifferent to the almost incomprehensible span of time, separating that distant future moment from this one. And in a very real sense, it becomes one of the closest things to genuine permanence that our species has ever managed to create, not because anyone specifically built it to last forever, but simply because we happen to send it somewhere that nothing ever really gets in the way. Now let's ground this in a few real numbers, because the actual science behind Voyager's endurance is worth understanding directly. Voyager carries 3 radioisotope thermoelectric generators, each one built around a core of plutonium-238, a man-made isotope that decays steadily, releasing heat that gets converted into usable electricity by solid-state thermocouples with no moving parts whatsoever, which is exactly why Voyager has run for close to 50 years without a single mechanical failure inside its actual power system. There is simply nothing there to physically break. But there is decay, and decay is entirely relentless. Plutonium-238 has a half-life of roughly 87.7 years, meaning roughly every 87 years, half of what remains simply stops producing heat at its previous rate. This is exactly why Voyager currently loses about 4 watts of available power every single year, forcing engineers to methodically shut down individual instruments one at a time just to keep the mission alive as long as possible. Sometime in the early 2030s, the very last remaining instrument will finally draw more power than the aging generators can still supply, and mission controllers here on Earth will permanently lose their final channel of communication with the spacecraft. At that exact point, Voyager stops being an active mission and instead becomes a monument, an object rather than an instrument. A thing simply moving through space rather than a thing actively observing it. There's no oxygen in interstellar space to cause rust, no moisture to cause corrosion, no wind, no rain, and no biological organisms of any kind capable of gradually breaking Voyager down. The primary long-term threats are cosmic rays, extremely high-energy particles traveling at close to light speed, and far more rarely, occasional collisions with drifting dust or debris. When a cosmic ray strikes a solid object like Voyager, it can knock individual atoms loose or subtly alter the internal structure of materials at a microscopic level. Over the span of mere decades, this effect remains genuinely negligible. But over the span of a full trillion years, it steadily adds up, gradually causing microscopic pitting across the spacecraft's outer surface. Even so, physicists generally agree this kind of slow atomic-level erosion is unlikely to ever destroy the object entirely, simply because the rate of accumulated damage remains extraordinarily slow compared to the sheer amount of solid material making up Voyager's overall frame. And collisions with interstellar dust remain a more sudden but statistically very rare threat, since interstellar space genuinely contains so little dust that meaningful collisions stay exceptionally unlikely even across a full trillion years of continuous travel. The overwhelming likelihood is that Voyager simply keeps drifting quietly and undisturbed, its shape degrading extremely slowly at the atomic level, while remaining fundamentally intact and recognizable the entire time. Now let's zoom out for a second, because the galactic merger itself deserves a much closer look, since it directly shapes where Voyager ultimately ends up. Andromeda is currently approaching us at roughly 250,000 miles per hour, and current projections suggest the two galaxies will make their first close pass in roughly 4.5 billion years. A pass that will not destroy either galaxy outright, but will instead begin pulling long streams of stars and gas out into sweeping arcs, a process astronomers have already directly observed happening in other colliding galaxy pairs elsewhere across the universe. The two galaxies will separate again after that initial pass, only to be pulled back together for several additional, progressively closer passes over the following billions of years, before finally settling permanently into a single combined elliptical galaxy, sometimes nicknamed Milkomeda, likely within 6 to 7 billion years from now. Both galaxies happen to carry a supermassive black hole at their respective centers, ours known as Sagittarius A, with a mass equivalent to roughly 4 million suns, and Andromeda's considerably larger black hole weighing in at roughly 100 million solar masses. As the overall merger fully completes, these two supermassive black holes are expected to gradually spiral toward each other over hundreds of millions of years, before eventually merging into one, an event that will release a genuine burst of gravitational waves spreading outward at the speed of light, though far too weak by the time they would ever reach something as small as Voyager to have any meaningful physical effect on it whatsoever. Here's a quick double hit of open physics questions, because 1 trillion years is long enough that even these start to matter. We do not fully understand whether protons ever decay, but if they do, current limits suggest it would take at least 10 to the power of 34 years, meaning Voyager's atomic structure stays secure across the full trillion-year span regardless. And physicist Stephen Hawking proposed that black holes slowly radiate away energy and eventually evaporate, though for a supermassive black hole that process takes far longer than 1 trillion years, meaning the black hole anchoring the merged Milky Way and Andromeda will still be there, essentially unchanged. And finally, one more milestone worth mentioning, the heat death of the universe, a hypothesized state in which all usable energy has evened out and no further physical process can occur anywhere. Current estimates place that true endpoint somewhere around 10 to the power of 100 years, so staggeringly larger than 1 trillion years that comparison becomes almost meaningless. At the 1 trillion year mark specifically, we remain within what cosmologists call the stelliferous era, the period during which stars, however rare and dim, still shine. A universe darkening and quieting, but not yet reaching the true final stillness that lies almost incomprehensibly further out along the timeline. And that, in the end, is the real answer to tonight's question. Voyager 1 will most likely still be out there in 1 trillion years, structurally intact but electronically silent, drifting either within the merged remains of the Milky Way and Andromeda, or somewhere in the emptiness beyond it, carrying its golden record through a universe gone dark and quiet around it. A small human-made object, never actually built to last forever, but simply sent somewhere quiet enough that lasting forever became, almost by accident, the only realistic outcome.